Okay, welcome to another edition of I Rant for 2 Hours. Today we're going to start talking about, well, we've talked a little bit about vectorization and functions up till now, but what we have not talked about is writing your own functions. So about half, a little bit more than half of today is going to be talking about how you write your own functions. And since everything we've been using in R up to this point is a function, being able to write functions should be obviously useful in some way. Part of the theme of today, too, is immediately after teaching everybody how to use loops last week, I want to tell everyone to avoid using loops ever again if possible. So this is your counterpoint to last week's lecture on loops. That is basically, don't loop. Sometimes you have to, but those should be the only times you loop. Okay, so I'm going to start, however, with a quick little aside. So, in any kind of R programming, any kind of programming you do in general, you should follow sort of a basic process in like writing your code. The idea is from the get-go, to write good code, you need to know exactly what it is you want your code to produce. If you don't have a clear idea of what your end goal is, you will never be able to write effective code to get there, because you're just telling the computer commands to produce something. If you don't have a good idea of what it is you want to produce, you obviously are probably not going to be getting out what you want. So, things you want to ask yourself as you're writing code, or before you're even writing code, you want to sit down and answer all these questions. You want to know, for instance, what is it you want to get out? Do you want a single value? Like, do you want a single number? Do you want a vector of numbers? Do you want a list of numbers? Do you want one observation per person year, per country year, you know, that kind of thing. You want to know exactly what it is that you want to pop out. Pretty much all programming problems that you'll commonly encounter that are not typos can be reduced to having some unclear idea of what your end goal is or what your beginning state is. If you don't have a clear idea of your end goal, you're not going to be able to write code to get there. But also, if you don't know what it is you're starting with, if you don't know what your data actually look like, you're never going to be able to come up with steps to translate it into even a clearly defined end goal, right? So you need to know both of these things, have a good idea of them before you even start writing any code at all. Okay. If you know what you've got, though, so if you know the structure of the data you're beginning with, and you have a clear vision of that final output, the steps to go from the original state to your final output are probably going to be relatively obvious. You might not know the exact functions and things you need to use, but conceptually you should know, oh, well, I have some data that look like this big, really wide block. I need to turn them into something that's much taller and much narrower. That is going from, say, wide data to long data. But if you know exactly what it is you want at the beginning, you can imagine a physical operation. You're like, well, I just need to rotate this stuff down and then figure out what functions can accomplish that. When in doubt, this is my procedure. I'm usually a pretty visual thinker. My procedure is if I have no idea what the intermediate steps are going to be to go from what I'm starting with to what I'm finishing with, I draw little diagrams. I try and sketch out what the data should look like visually, not as like, you know, data entries, but just like the shape of the data. If I know it's a really wide line and I've got like 5 things in it and I want to turn it into something tall and put those 5 things there, I will draw that out. I'll be like, okay, well, my data look kind of like something like this, and maybe for a single observation I've got like an ID, but then I've got maybe, you know, I've got like 3 objects like this, and I somehow want to make this thing go to be like this ID here, and then I want to get like, right, line all those things up in some way. And I think to myself, well, as a physical operation, how could I disassemble these points of data and just make them go, right, into the spots that I want? And if I can figure out a process that I could do that by hand, I can probably figure out a way to write the code to do it. I just draw a diagram. I'm like, well, I want this crap over here, I want that crap over there. Do that, and then I'll figure out some clunky way to do it in code. Maybe later I'll make it more efficient. But by drawing the diagram, I have a good idea of what has to happen. I'm like, well, this thing needs to go from covering like 2 rows of my data to covering all 5 of them. Then these things need to become their own individual values here. And so I can be like, well, I can separate this thing out into one piece over here. I can separate these things out into order as single ones. and then I just stitch these together and then stick that to it, and I will end up with this object over here. Those are all discrete operations on my data I know how to do, right? In a loop, I could be like, well, I can just extract this object, then separate this into one big, put these a vector, rotate it down, paste them together, C-bind them together, I come up with something. If I do it visually, I can usually figure out how to do it. It might be clunky and dumb, but it'll work. If I can't think of a way to do it visually, I have a problem, which usually means I don't know what I'm starting with or I don't know what I want in the end. Okay. If something is complex, so if you have a beginning state and an end goal, but the operation to go from one to the other is really complex, come up with intermediate steps between that, right? Work backwards and work forward at the same time until they meet in the middle, and you might have some idea how to put it together. If it's really complex and it seems irreducibly complex, you're probably wrong. Look for somebody else who's done the same thing. Search online for some similar operation, find somebody's code. Sometimes things are really hard, but there's always intermediate steps you can come up with, except in very rare cases. Okay. So anyway, vectorization. If we remember last week, we tried to find the means of all the different variables in the Swiss data set, and I provided you with an example that was a loop, where we looped over, oh, get one mean, print it, get another mean, print it, whatever. I did a whole bunch of different means, or assign them to a vector and print it. Well, for that, we could write a loop. Yes, it would scale really well for like 200 variables, but you're still writing a bare minimum of 3 lines of code or something like that to start the loop, to assign something and to print it. Well, a better way to do that would just be to call on some function that already does this thing. For instance, call means. Rather than writing a loop to get all the means, I can just say call means Swiss, and it prints out a vector, a named vector, where each element is a mean, and the name of each of those elements is whatever that variable was. That's the means of all the variables in the Swiss data set, right? I don't have to worry about pre-allocating some vector. I don't have to worry about writing a loop. Writing a loop is less code than doing every single operation manually, but it is more definitely than doing one function call that sort of takes care of everything behind the scenes, right? Okay. Vectorization is about avoiding writing loops. Good R style is not writing loops. Loops are considered bad style in R because they tend to be fairly slow. They're not actually super slow. If you do them right, they're about as fast as loops in Python, but loops are still in general kind of slow compared to vectorized things. The thing with loops, though, is that loops are incredibly powerful, and basically any operation you want to do on your computer, you could probably figure out a way to write a loop to do it. Loops are just the universal application for anything. That's a problem, though, as it means you'll always think about writing loops, and loops are really, really, really slow, and you write more code to do them. So, yeah, vectorized commands tend to be very compact and faster. I'll show you in a little bit how much faster, or at least maybe I did that last week, actually, I can't remember. But anyway, whenever possible, use some vectorized command like call means. Or, for instance, vectorized commands, everything inside of dplyr is already a vectorized command. Everything we've been using is vectorized. It's much faster than any alternative you could do in a loop, except for very limited special cases. Sometimes, however, there's no functions that exist to do what we need. So maybe we don't need call means, but we need some obscure thing. Maybe we need something like, well, I want the mean, but only the means of the middle 50% of observations in every column. There's no specific function that can do that, right? You might be tempted to write a loop to do that, and that would be okay. But I would say that's only okay if you're going to be doing some fast, one-time operation on relatively small data. If you're going to be doing something repetitively, or you're going to be doing it on larger data sets, loops scale poorly in R. It's going to get slower and slower, and the more times you keep using that, the more you're sort of compounding your problem with performance, right? Okay. If your data are big, or you're going to be doing that operation repeatedly, what I recommend doing is writing your own function to do that, which is itself vectorized. It'll be faster, it'll be more efficient, it'll be easier to use repetitively. So, how do we write functions in R? Turns out it's really, really easy, and we've sort of been doing more or less this all term without really noticing. Okay, so some examples of existing functions that we've used in this class that we could write equivalents to are things like the mean. The mean takes as an input some numeric vector. It outputs a single number, which is the mean of the vector of numbers you gave it. Filter in dplyr takes as an input a data frame as its first argument. When we're piping something into filter, we're sending the data frame in as its first argument. And then it takes some logical conditions as its next argument. Something like, oh, country equals Albania or something from Gapminder data is a logical condition. Its output is a data frame with rows removed if they don't meet that logical condition. Reader, read underscore CSV is a function. It takes as an input some file path on your computer and may take arguments for things like variable names or types. The output of read.csv is a data frame containing info read in from that particular file. So what do all these functions have in common, and all functions in R, is that they have some sort of input and some sort of output, and they may have some arguments that change how that input turns into an output. All a function is something that translates an input to an output. Okay. Why might you want to write your own functions? Functions are good for encapsulating sort of repeated actions, letting you do something you want to do many, many, many times without repeating the code over and over again. Some examples we're going to do in class today for functions are, given a vector, compute some special summary statistics. Maybe you have a set of summary statistics you always want to run on something. Maybe you basically want to make your own version of a stata-style summary command or something. You always want the same summary table. You can just write a function that will always generate the summary that you want. Maybe, given some vector of data and a definition of invalid values, you want to replace them with NAs. This might be common if you have some sort of data set, say, generated by a survey you designed, and you know that values like 998, 999 are missing or negative values. You can just make a function that will automatically replace those values with NA within those ranges and for those specific variables. Another thing you could encapsulate in a function would be templates for your favorite ggplots you want to use in reports. Maybe you have a very specific style of ggplots you like to use. I know I have a specific style I like to produce, but I don't want to keep writing those big blocks of ggplot code every time I want to generate it. Instead, what I want to do is I just want to send a data set to that function, or maybe I just want to say, plot this variable, and it automatically knows what data set to go to. You can make templates and make them as functions that will automatically call ggplot, shape your data, produce it and all in a little function call. More advanced things you might want to use to generate functions for are things like parallel processing. By default, in R, much like Python, everything is actually being done only on one core on your processor. If you know, most people's computers nowadays have 4, 6, 8, 20 cores, depending on what you've got. Well, multiple processors make things faster, but in a language like R or Python that is not multi-threaded by default, you probably have to do some manual adjustment of functions or making your own functions to make it fast. If you work with big data, it's really important to learn how to do this because you can speed things up massively. Also with some Bayesian applications where you can do sampling across multiple threads. Another thing you might want to do is generate functions using functions. So sometimes you want to do something like, example I have is I put together an R package to generate homeworks for this class that would grade themselves. Well, to do that, I wanted to be able to call on a function that would generate functions to check the grades within those homeworks and then output it. That's pretty advanced. You're like, well, I have a function that writes other functions. That actually becomes quite common in advanced R, that you have functions that generate other functions to run on data. I forget there's a computer science general term for that, but I forget at the moment. Another thing would be, say, this isn't about writing a function to do this, but rather packaging your functions. You might want to make custom packages in R that will contain all your functions. I have a lot of personal functions I like to use inside of different projects that I work on, and I might want to package these all into an R package that I would load all on my different computers. At this point, I'm not presently doing that because I just synchronize all of my installs across machines, but if I wanted to make it portable or wanted to give people in this class, say, functions I wanted to use, I would do that. And writing packages is sort of an advanced R skill that's useful, and it's all based around functions. And sort of every R package we use in this class is constructed exactly using the sort of methods we use in this class to make functions. Everything we've used in this class that wasn't built like right into R was just written by another person who at some point learned R in much the same way as you did, wrote a package, wrote a bunch of functions, packaged together, and made them so they can be downloaded online, like dplyr, ggplot, all of those. Those are just written in R using the exact stuff we're going to learn today. Okay, so here's an example of a simple function that you might write and use yourself. This is a function that takes a vector as an input, and as an output, it will return a named vector of the first and last elements of its input. So how does this work? We're going to call the function first and last. So you do assignment on a name to make a function the same as you make any other object in R, because functions are objects in R. We're going to say first and last is a function. Function is the function that makes functions. Yeah. The arguments go here in parentheses and then open brackets. Inside of here is what you are going to have that function do when it runs. So what this says here is that, okay, we are going to have some input we're going to call x. We're going to assign to the element first, something we're going to call first, the first element of x. So x subset 1 means get the first element of x. Then to something called last, we're going to assign x length x. That's just a shortcut way to get the last element of something, because the length of an object is the number of elements it has. So if it has 8 elements, length x will return an 8, so we'll get the 8th element of x. So I get the last of something. And then we're going to return, that is, return specifies the output. We're going to return the first and the last, and we're going to name those things first and last. How do we use this function? Works like this. I say the first and last, which I just created there, I give it a vector, 4, 3, 1, 8. What does it output? Exactly what I asked it to. It outputs the first element and calls it first. It outputs the last element and calls it last. Right? So I created that function right there. I can just give it inputs. It will produce things. Okay? I have questions about this general structure. I'm going to go over it a few times. It kind of looks like a loop. And then instead of saying like for I in something, we have function x and then brackets. And inside the brackets are all the guts of the function that does stuff. Okay. So what happens, however, if I give first and last a vector of length 1? So if I give first and last 7, it says the first element is 7 and the last element is 7. This is true. Its first element is 7 and its last is 7 because it only has one element. We might consider that to be pretty stupid behavior. We've given an object that the first and last is the exact same element. It still returns 7s. What happens if we give it something with length 0? So it doesn't have a length. It doesn't have any elements. It just says, oh, NA first. It doesn't say anything for last. The function doesn't have errors or anything. It just kind of fails in an ugly way and doesn't do anything. Okay? Well, an important thing for writing functions is sometimes you want them to check for problems, so you can build in error-checking functionality into your functions using if and else statements, which we learned last week. So, a common thing that most functions you would write if you're going to reuse them in multiple applications would be to have them check to make sure the correct input is being given to them. So this first and last kind of assumes, or at least we're building around the assumption, that we're going to give it something like a numeric vector or a character vector, something that has an actual length and contains some values, right? So let's make sure it gives us an error message when the vector is too small to be a valid input. That is, if something has no length, we probably want it to kick an error message. What we can say is inside this exact same function, we still have the same body. This is the same thing. First is 1, last is the last element, it returns the same thing. But before it runs this stuff inside the function, we have a check. So it says here, at the very beginning, the first thing that happens is if length x equals 0L, L is how you specify integers in R, so 0L just says if length is equal to exactly 1, the integer 1, then that means there is no length to it. So I'm going to say stop, the input has no length. Stop will generate an error message and cease running something, whether it's a loop or a function. It's one of the most common ways to generate error messages inside of a function in R or inside of a loop. If, however, the length is not 0, so if it has any non-zero length, length in R can only be positive, so this is basically a way of saying as long as it's at least length 1, just behave normally. So if this passes, do that. Or if this is true, do that. If not, do that. Error checking. Does that make sense how that works? This is what the output would be. If I give smarter first and last a vector of length 0, it will kick out an error saying, error in the function name, the input has no length. That was the error message I told it to give. If, however, I give it the original vector of 4318, it just works normally. Okay? That's how you add input checking to a function. Make sense? Okay. So, if you type a function in R, any function in R, any single function in R, if you type it in without the parentheses in your console, like you could type in filter, you could type in summarize, anything like that, it will display the entire contents of the function. That is because R is open source and most of the code in R is written in R, so you can just crack it open and look at how those functions work. So for instance, if I typed out the function I just created, smarter first and last, into R, without the parentheses, it just dumps the entire function and shows me all the code that was used to generate it. Okay? You can also do this by putting your cursor over any function in R, anywhere in your like syntax or anything. Hover your cursor over it and hit F2. It will crack open a little script and show you everything in the function. When you're a more advanced R user, if you're working on using some kind of function that kicks out a weird error message you don't understand, or if it just has a bug in it, you can open up the functions and say fix the bug if you can figure out where it is, or edit the code so it gets around the bug. Just because you can open all those functions up and look at it. I do this pretty regularly because I've got some old software I like to use in R, but it's all out of date. Nobody updates it, so I have to keep modifying it so it works on new stuff. It's a little advanced, but you'll get there eventually if you keep that. Okay. So, what is the anatomy of a function? What is its construction? So, functions, like any other object in R, they have a name. The name is whatever you would assign the function to, right? You can have anonymous functions in R. Those functions that have no name, and we're going to talk about how you use those in a bit. Those are functions you sort of call on the spot and never reuse because they don't have a name. They have arguments. So the arguments for a function go inside the parentheses when you assign the function. For instance, argument 1, argument 2. These are things that you can pass to the function to affect how it works. That can be passing input to it that's going to be modified in some way, or it can be flags, little things you can swap to change its behavior. For instance, in mean, we have na.rm equals true to get rid of nas. That is just an argument we add to the function. We could specify it ourselves. You can set defaults when you make a function like this. If I say argument, whatever, argument 1, argument 2 equals some value, that becomes a default. If you or some other user does not specify a different value for that argument, it will automatically use whatever you've put there for default. So for instance, the mean function in R, its default is na.rm equals false. It doesn't remove nas by default. But it actually in the function has to say na.rm equals false when it was written, so that default is there. If you don't give something to default, the function is going to ask you to give it and provide an error message when you don't give that function something. So normally if you're going to write some function that takes a few arguments, you'll probably set defaults for all but one of them, and the one you probably won't set a default for is, say, input data. If you have some function that works on a whole data frame, you want it to always require a data frame, but it might have a bunch of other defaults. You say just always do this unless I say otherwise. Okay? Values for like argument 1 and argument 2, if you set those things with the default, those values will not exist outside of the function. Anything that you have in the arguments or anything fed into a function only exists inside of the function. This is unlike loops where, say, we specify I equals 1 to 10. When a loop finishes running, whatever you finish that value of I at persists and exists outside of the loop. This is not the way functions work. All intermediate objects that were made inside of it, whether they are arguments set to defaults or data sets created inside of a function, any of that only exists inside of the function. Once that function completes running, all that stuff will be deleted from memory except for the output from that function. Okay. And then the body is the actual operations you want to do inside the function. There could be like a couple operations, there could be hundreds of operations. There could be other functions inside of that function. Very often in something like dplyr, if you open up dplyr functions, you'll see many, if not most of them. In there, they're just calling on other functions. Then if you follow those functions, you'll see those functions call on other functions, and those functions call on other functions yet. Like, it all kind of nests all the way down until you get to base R functions. Lastly, there is a return value for a function. you put the output, what you actually want to come out of the function, inside return. Return is just spit out this one thing. This could be a vector, list, data frame, another function. It could be nothing. Sometimes you want to run a function and actually have it output nothing. It's not too common, but sometimes you want to do that. An example of a function that outputs nothing is rm, remove. It just deletes things, but it doesn't spit any output out. Yeah, if you do not specify a return for a function, the last thing calculated by the function will be generated as output. Very often that's what you want, but sometimes it's not. Okay, any questions about this? Okay, so here's an example of another function. Maybe you want to have more detailed quantile information than summary gives you, and maybe you want it to have interpretable names. We can write a function that gives a lot of quantiles for some vector. It could look something like this. I'm going to call the function quantile report. I'm going to assign to it a function. The function is some function of x. X is kind of like I in a loop. It's an arbitrary thing. I could name this whatever I want, but when I want to specify the input, if this is x, I would want to say x equals whatever the input is. If I make this k, I would have to say k equals that, right? This is, yeah, like any other arguments in a function, they have specific names you can name. I also want this particular quantile report function to have an na.rm command the way like mean does. I'm going to set its default to false. So by default, it won't remove NAs. Inside of this function, we're going to create an object called quants, which are going to be quantiles of something. I'm going to assign to that the quantile function. So quantile is just a function that, given a vector and some set of probabilities, will generate quantiles of those. I'm going to say quantile of x. So our x input to this function is going to get passed down to quantile here and run inside quantile. And I say na.rm equals na.rm. What that means is whatever value is set for na.rm when I run this function just gets passed down to this location and fed to that quantile. So if you have a function inside of another function, you can just pass down arguments like that into those other functions. Anything given to this function can just be given to something else inside. So you can nest functions inside of each other. When I do data cleaning for projects, I usually will take like all the dplyr chain syntax that I would have you guys do in classes, like the previous homework. You'd chain together a whole bunch of dplyr commands. I take those dplyr commands, I put them inside a function, and go stuff that function in some other file. So when I actually do the cleaning in my RMD files, I just call some function that is like clean data, or like load data, clean data, reshape data. I'll call like 3 functions at the top of the RMD, and then everything else is just plotting stuff. So you could put like all that dplyr stuff inside of a function. You just make it like, oh, give it this data set, and then at the end it would return the complete data. It's a little more advanced than I'm going to show you guys today. Anyway, then I'm going to have some probabilities, which I'm going to set manually. These are just constants. I'm saying, okay, I want all these different quantiles. I'm going to give them names, which I'm going to assign to the quants, and then I'm going to return the quantiles. So if I do a quantile report on 10,000 observations from a standard normal distribution, we see something like this. I now have a named vector that has bottom 1%, 5%, 10%, 25%, the median, top 25, 10, 5, and 1, which were just generated by these quantile values, named with these names here, and then I just give it some data, it spits it out. If I generated this with missing values and I ran this, it would give me an error saying there's NAs, it would just return an NA. I have to say na.rm equals true. But I don't have to specify na.rm here because it has a default, right? It just kind of works. And we know it works correctly because by using the standard normal distribution, if you know what a standard normal distribution's quantile should look like, we know these are correct. Any questions about that?
Sorry,
Yeah.
what does R norm?
R norm means R for random generation of data, normal distribution. And then if I give it 10,000, let's say generate 10,000 observations, the default for R norm is to make a mean 0 standard deviation 1 data set. So this is 10,000 observations, mean 0 standard deviation 1. So this is a standard normal distribution by default. You could give it other arguments. Yeah, that's how you generate random data. I show that a little bit if you go back to the regression, the optional regression homework from week 4. There's a lot of random data generation in there, which is a good resource if you want to do that. Okay. So, there are ways to, instead of using a loop, take some function that normally operates on, say, one vector at a time and apply it to many different vectors or, say, many columns of a data set. These is a family of functions called apply functions. As a side note, dplyr is actually named that way because it is data frame apply. It's basically a wrapper or a way of doing apply functions like these specific to data frames. The plyr package is a universal way of doing these applies. This I'm going to teach you is the base R way of doing applies because they're sort of universal and actually pretty easy to use. So, lapply is probably the most commonly used apply function. What lapply is used for is to apply some function over a list of any kind. That is, I want some function and I want to use that function on every element of the list. Data frames, their columns are elements of a list, so you can use lapply to do some function to all the columns of a data frame. And this is a lot easier than doing a for loop to do the same thing. It's also like 100 times faster. Let's say what I want is I want to do my quantile report function I just generated on the last one, and I want to apply it to every variable in the Swiss data set. I could say lapply Swiss data set. The function I want to apply is quantile report. That is all I have to do. The output from that is going to be my quantile report for every variable in the data set. I've truncated the rest, but guarantee it ran on every single variable. This is a lot easier than running a loop. You just say, do this to all of the things in that. It takes care of the rest. And it does it really fast. If there were 40,000 variables in that Swiss data set, it would still be instantaneous. A loop would not be instantaneous. Okay. Anyone have questions about that syntax? It's worth messing around with, because it seems like you should have to give it more options than that, but you don't. You just say, do this thing to that, and it does it. Okay. One downside to lapply makes lists, and in this class we've basically worked entirely with data frames. Lists are a little annoying to work with. If you're coming from some programming environment like Python, you're like, I do everything in lists anyway, so I love lists. Good for you. Use lots of lapply. But for us, we generally like working with data frames or something that you can treat kind of like a data frame, which is a matrix. sapply is simplified lapply. What it does is it takes the output of lapply and makes it into a matrix. That is, it takes every element of this. So an element being like this entire thing is one element of the output, this is one element of the output. It turns those into columns in a matrix. So sapply, quantile report, is doing the exact same thing as the lapply. The difference here is that now each variable has its own column, each variable from the Swiss data set. Each row is now one of those quantiles that were specified by the function. Right? So this is a matrix output instead of a list output. It's the exact same operation, the exact same syntax. If you want a matrix, you use sapply. If you want a list, you use lapply. You could coerce this into a data frame by doing as.data.frame, and this will turn into a data frame if you want that. It's not really, wouldn't make a lot of sense as a data frame, because, I mean, it's variables here, but these don't make sense as rows. But still, you can do what you want. Okay. There is also a generic apply function that can be used over matrices or data frames or vectors. It can be used over any object in R, arrays. You can do it over multidimensional arrays, whatever. You can just tell it exactly what function you want to apply and what margin you want to apply it to. So if I say apply Swiss data set margin equals 2, the second margin of something is the second dimension. The second dimension is columns, usually in a matrix. The first dimension is rows. If we have a multidimensional array, the third is depth, so on and so forth. And then apply the function quantile report. The output of this is exactly the same as the output of sapply. The difference here is maybe I wanted to run it over the rows instead of run it over the columns. I would say margin 1, and it would do some calculation across all the rows. Maybe I wanted to get quantiles across rows instead of across my columns. You just say margin 1, run the exact same command. Apply functions like this are considered good R style, and R was designed to use these apply functions instead of using loops. They are much faster, they're compact, their syntax is very compact. They can be kind of opaque, because you're giving it very little orders and it's doing a lot of operations in the background, but they are tremendously powerful. Behind the scenes, things like dplyr are basically doing these apply commands, but they're just breaking them down into complex parts. Yeah?
So I supply in the default is by column.
Mm-hmm.
So can I supply also by row?
With sapply?
Yeah.
No. So sapply, so the way lapply and sapply work is they run some function over the elements of a list. Well, the thing is Swiss is a data frame. The list elements of a data frame are its columns. So it doesn't make any sense to sapply or lapply to say run it over its rows, because the rows are not the elements of that list. Only the columns are. However, you can make apply do it over rows. You can say, okay, I want to run over margin equals 1. It will do it over the rows. The way it does that behind the scenes is to actually convert your data frame into a matrix, transpose that matrix, convert it back to a list, and run it over all the elements of the list. It's actually a complex operation. But that's just because the way lists are. Data frames, those columns and rows are not columns and rows. It's actually just equal length list elements. Yeah. So yeah, if you want to do something over rows, use apply and say margin equals 1. Or do dplyr functions that run over rows. Dplyr just kind of lets you ignore most of the stuff and do it, but dplyr is not always good at doing row-wise things. Actually, in fact, row-wise things are, in general, hard to do in R because usually calculations don't make much sense to be done across rows. You should instead probably convert them to columns and do column operations on them. But it depends what you want to do. Any other questions? Okay. So, an example we might want to do using these sorts of functions is maybe we want to bucket our variables into data or into groups based on quantiles. Very often we want to do something like generate ordinal variables with some kind of cut points. Right? For instance here, I've got an example 6 people with a few different incomes, and I want to assign them to different buckets of income. So people who make a smaller amount of money are in income bucket 1, people making more in income bucket 3, 4, 5, something like that. Discretizing your data. Okay, to do this, you could use the cut function built into R. There's already a function in R that does cuts into things, but to use the cut function, you'd have to specify specific cut points or tell it the number of buckets you want to split the data into. Instead, what we want to do is let's make a function, I'm going to call it a convenience function because it's basically just giving me a shortcut to do this, where I cut the data using the quantiles, split it out, and return integer values. So this is going to split the data up by quantiles built into the function with defaults, but I could specify them manually if I want, and then spit out some categorical variable, something that I could make into a factor to have like a factor variable or an ordinal variable. So I'm going to call this function bucket. Bucket is equal to function. It takes some x, some input, and then it has quantiles. By default, its quantiles are going to be the first third and the second third, right? Then what I want to do is I want to set a low extreme, a bunch of quantile points, and a high extreme for it. So I'm going to say I want my breaks in my data to be split like this. I'm going to start at the minimum of the data, minimum -1, because these things are going to be like they're inclusive. So I basically want to have my data at this end of the distribution. Let's say all my data are here. I want to make sure I get the last observation, so I'm just going to reduce my minimum just slightly. So we'll always capture all of them. Do the same thing at the maximum. I want to go out to here, so I just move this out a little bit, and that window captures everything. So that's my minimum and my maximum. In the middle of this, I'm going to use the quantile function. The quantile, I'm going to give x to quantile, and I'm going to say probabilities equals the quantiles I present here. So by default, what this is going to do is it's going to find the 33.3rd percentile of my data, return that value of x. It's going to find the 66.6th percentile, return that value. Or if I gave a vector of quantiles that was like 100 different quantiles, it would produce those values of x in the middle. but still have a minimum and a maximum that go beyond the minimum and maximum of the data. This makes sure I lose no data, but I can divide it up into an arbitrary number of buckets. I could give it one number, I could give it an infinite number of numbers. It will just adjust how many breakpoints there are. Then I just want to return, run the cut function I talked about here, cut my original data I give to it, but the breaks are going to be these new breaks in the data I calculated right here. And I say labels false because I don't want to label the data based on the actual x values. You could mess with this and see what labels equals true does. It's kind of weird. So it works like this. If I generate some random data, I'm going to call it random data. It's 100 observations from a standard normal distribution. I'm going to create new bucketed random data. I'm just going to say bucket, using the previous function we just created, random data, and I want it broken up by these quantiles. I basically want a division at the 5th, 25th, 50th, 75th, and 95th percentiles for my buckets. Then I plot it. I just say bucketed random data and the original random data. So the buckets are 6 values. 1, 2, 3, 4, 5, 6, which should make sense. 1, 2, 3, 4, 5. There's going to be up to this point, between these, between these, between these, between these, and above that point. Right? 6. So the categories are 1, 2, 3, 4, 5, and 6, which correspond to these original values of my data. You can see everything is bucketed into these groups. There isn't crossover. Like, it kind of looks like there's overlap, but there isn't. We've bucketed our data successfully. So this is a discretizing function, which is flexible for any arbitrary quantiles. Maybe you want to explore like different breakpoints for an ordinal variable to see how it performs in a model or something like that. You could make it like automate the process of cutting your data up into some variable or just some like ordinal variable, running a model, getting some output, and then do that for 100 different specifications of that variable or something like that using the code we used for looping last week. Make sense? Okay. Here's another example. Let's say we have a bunch of data where a bunch of impossible values occur. So let's say we have data from schools where we have some school ID, but then we have the percent passing exams and the percent on free lunch. And our data looks something like this. Well, we know that if something is a percent, or actually it's a proportion, we have proportions. Well, you can't have a negative proportion, so this is probably some kind of missing value tag. You also can't have a value over 1, so these 99s are probably some sort of missing value. Here's another negative value, here's some 99s. We know those are impossible values for this, so we want to sort of clean them out. We can write a function to do that. So, our goal will be to give some input, some vector of x values, have a cutoff for the low values and a cutoff for the high values. We're just going to say, okay, valid data exists between this low and this high. Everything above or below that should be replaced with an NA. So the output is a vector with NAs in the extreme places. That is anything below low and anything above high in X. You could do a function like this. I'm going to call this function remove extremes. So remove extremes is a function that takes X, it takes a low value, and it takes a high value. And it works like this. I'm going to generate an object called X no low, which is just going to be X with the low values removed. And this is just if else. I say if else X is below my low value, assign an NA to this. If X is not below my low, just keep it X. So this is saying drop any values of X that are below low and keep the rest. Then I say X no low, no high is X no low, it already has the lows removed. If X no low is above high, so above our input value, replace it with an NA. Otherwise, keep it the original value of X. Then return X no low, no high. So if I run remove extremes on my school data per proportion passing exam, I can say my low is 0, my high is 1, remove any values below 0 or above 1. What do we get? NAs in the places that had high or low values. So it's a little data cleaning function that handles extreme values in a data set. Neat thing about this is it's flexible. You could have different variables, might have different lows or highs, you could adjust it. Maybe you don't actually know what the valid values are and you got to poke at it, you could just adjust them until things look right. Make sense how that works? Any questions? Okay. So, the dplyr functions mutate at and summarize at will take an argument functions. This will apply some function, including functions, say, you've made yourself, and apply it to every variable that you give as a name to vars inside of it. So if I take my school data that I generated before, I could say I want to mutate at all the variables except school. This is the same syntax as the select function in dplyr. So to every variable except school, I want to run my remove extremes function. X is equal to period. I'm just going to pass the whole data set to it. dplyr already knows to remove school for me. I don't have to specify anything else. Then I say low 0, high 1. What this will do is it will run my remove extremes function with these arguments to all of the other variables in the data set. So the invalid values have been replaced with NAs in both of the columns. Let's say you had 500 columns in your data set you needed to remove extreme values for. You wouldn't have to change this code in any way. It would just do it for all those 500 columns. Right? This is a vectorized way of doing it within dplyr. Works a lot like apply, because dplyr actually is basically just apply. Does that make sense? Any questions about this? It's a compact way of avoiding writing lots of mutate functions.
Sorry, could you repeat the mutate? Sorry.
Yeah, I was just saying, mutate at basically just does repetitive mutate calls. So instead of saying mutate PR passing exam equals remove extremes PR passing exam, and then do that same thing for PR free lunch, I can do as many columns as I want in a single call. One of my most common operations in data sets, because I do a lot of structural equation modeling, is I need to standardize a lot of variables in my data set, but not all of them. Very commonly, I don't want to standardize any discrete, any factor variables, anything like that. Every numeric variable might need to be standardized except for ones that are pretty close to normal. I would do something like mutate at vars minus my ID variables, minus my factor variables, whatever. Then functions standardize, and it would standardize the entire data set except for the variables I don't want standardized. Really common operation if you're working with either structural equation models or hierarchical linear models that don't behave well when things have very large differences in variances. Saves you a lot of writing code. Just shortcuts. Okay.
Funds is the same as fund equal in apply.
Yes, pretty much. It's not exactly the same, but it is. It's a it's its own function, and it's just because of the way mutate at works. So the way mutate at is actually working is vars down here actually goes out and calls the select function and runs select and then generates an intermediate data set. Funds here actually takes whatever function you write here, converts it into a string, does some weird stuff behind the scenes to actually run the function and then return it back. It looks really clean and easy, but I've looked into the code and I'm like, whoa, that is bizarre. Yeah, so it's kind of like funds equals, but instead you put whole functions in because you can put many functions inside of it. So you can't do like equals and have a string of functions in like apply. Mutate at, you could easily give mutate at like 5 functions here, and it would run all 5 of those functions on every variable in the data set at the same time.
Why is it the x is equal to dot?
X is equal to dot. It's a great question. What's happening here is, so if you remember, you can replace, in dplyr syntax, by default, when you pipe data in, the data normally go into the location of the first argument in any function. However, if you put a period somewhere, the input from that actually gets piped to the period. The way mutate at and similar functions work is you specify where inside the function you're going to use you want to actually put the input data. So this is saying, okay, if I had a normal vector, I would put the vector there. However, I'm going to be running on a whole bunch of different vectors. That period indicates to mutate at that is where the data should go, so each column should go in this location to run it. It's just the syntax that they use. Basically what happens is mutate at detects where a period is, and once it's done selecting these data, it will stick those data in wherever it finds the period. You could use multiple periods too. Yeah, so you could put you could put it in 2 different locations. Maybe you want to standardize your data manually, and you say, I want to put it into mean, and I want to divide it, I want the period minus mean period divided by SD period would standardize your data. That sounds really weird, but trust me, it works. The period replaces where you'd normally have an input to that function. I would recommend playing with it to see what happens. But yeah, that's just kind of replacing your input. Yeah. It's basically saying, take my school data and put it there, but it's not exactly what it's doing, because it's saying put each individual column there one at a time and run them all. That's just the syntax it uses. There's no magic to it.
And the remove extremes is basically saying put NAs.
Is do what?
Put NAs.
NAs. Yeah, so the remove extremes is just doing this. So it's replacing the low values with NA and the high values with NA, because we wrote the function. Yeah. Does that make sense? Okay. It's a little weird, I know. This is one of those ones you kind of mess with. I might recommend, when poking at a homework or something, try using mutate at and seeing what happens if you use it on multiple columns or something. You kind of just got to get used to its syntax, because the syntax is a little bit weird. Yeah?
Can we use apply to replace this command while did not do anything with this factor?
So if you wanted to do an apply to do this exact same operation, so basically if you want to apply and remove extremes from these 2 columns but not this one, the syntax for it is going to look something, okay. It's going to be pure, to do this in pure base R, it's going to look a little different than what we've been doing, but it's actually not that complex. It would be something like, let's say the data frame was called data. You would just say, data frame, let's say, -1. And then we would say, apply to data -1. Function equals, say, what was it, remove extremes, or whatever I call it. So I'm just going to say it's that. Remove extremes, and then you could have to give it arguments, and I believe it would be in args. No, it's in... Oh, you just give it right here. Removes extremes, low equals 0, high equals 1. So what this is doing here, which is a little bit different, is basically saying, okay, we don't want to do this operation to the first column, so I'm not going to give that first column as data here. I'm also not going to write to that first column, right? So I'm just using subsetting on both sides, run those operations, and do it there. Yeah. If you know how to use apply commands and stuff, that would seem obvious in native if you're a base R user, but it's a little bit, mutate add is nice because you can throw it into this chain of pipes and stuff like that. Yeah. I use a lot of apply commands, especially when I'm not subsetting my data. I usually would use mutate add if I am subsetting my data because I prefer the syntax for subsetting here over doing it, especially because I'm usually subsetting by names and I like to be able to arbitrarily shuffle my columns around. You could do that and subtract by a named element from the apply, but it's a little bit more of a pain. Great question. Yeah, so this is equivalent, but, I prefer the syntax. Okay, so a quick aside about standard and non-standard evaluation. So dplyr by default uses something that is called non-standard evaluation of variables. So if you've noticed, whenever you do anything with a variable in dplyr, you can just use its object name. So you can do something like for instance here, I could just say vars minus school, but in here I can do functions, well, I'm not calling it a direct argument, it's like vars minus school. In most functions in R, instead of doing minus school, you'd have to do minus and then school in quotes. That is called standard evaluation. Being able to directly call in an object without actually using the object. We're not using the school object here. We're just using its name. This is called non-standard evaluation. It's actually doing something programmatically that's pretty weird. It's turning that quoted name into a quoted name inside of the function, running some stuff and spitting it out without us ever noticing. It makes it really easy to write code, but the first time a programmer who's used to this sort of style of language looks at that, they're like, how the hell does that even work? It's a weird type of evaluation. Anyway, that type of evaluation, the no quoted one, is actually really hard to use inside of a loop because normally you're looping over like a named vector. You can't loop over a vector of object names. They have to be quoted. They have to be strings. So you couldn't, for instance, let's say you wanted to run a loop that did a whole bunch of different mutate ats. You wouldn't be able to feed it an unquoted object name because you can't loop over like a vector of actual objects. You can loop over their names. Okay? So a neat thing that was added relatively recently in dplyr is that in most dplyr functions, you can give it either quoted or unquoted names of things and it will work exactly the same way, which is nice for building loops. So if you happen to look at the data downloading horror story that was linked off of the website, there was one location where there's a mutate at command made where the variables that's given to it is actually a vector of character names of something, and it still just worked as if we'd given it the literal object names that don't have quotes. That's some neat functionality. Virtually all of you will never have to do that, but this is one of those slides that you can hopefully remember it is possible to do that if you have to do it programmatically. Okay, so anonymous functions. In something like dplyr, or in fact in something like apply functions, you don't have to name a function. You can just put a function inside of it that is called an anonymous function. So if you put code like inside of, say, summarize all. Summarize all says run a summary on every column in the data set, no exceptions, just summarize everything. You could give it a function in here without actually specifying the name of the function or manually writing the function. You've actually been doing this a lot in mutate, you just never noticed it until now. You could say something like, summarize all, the functions I want to run are mean of our data, or each column, divided by standard deviation of those data, and run it. You notice I don't assign a function. I don't say like function x, and then inside the body is mean x divided by sdx. Summarize all and all the dplyr things will just let you arbitrarily create what is essentially a function. This is two different function calls that we normally have to nest inside a function to run. You can just give it to it. It will make its own function inside of that summarize call to do it, run that operation, and spit stuff out. So this generates the mean divided by the standard deviation of every single one of those variables. Okay? This is called an anonymous function. It's anonymous because we never gave it a name. It is still a function that we're running. To see how it is a function that we're running, this is the way you have to do it inside of an apply function like lapply. In lapply, to do this over the Swiss data set, we would have to say, I want to lapply to the Swiss data set a function. The function is a function of x, mean of x divided by SD of x. This is actually me using a function call to generate a function. It's just automatically right off the bat feeding the Swiss data set into it piece by piece. This is an anonymous function because we have never named the function, but we're still using a function, making it, running data through it. We're just discarding it immediately. You didn't realize it probably before, but every time you did like a mutate call where you took one variable and divided it by another variable, or one variable and divided it by something, you're actually making an anonymous function. You're making a function, you're just not giving it a name. You're just running it and discarding that function because you don't need it anymore. We do this all the time. Does that make sense? It's okay if it doesn't, because that's kind of weird. But yeah, it works. Okay, here's another example, something which you're actually going to use in your upcoming two-part homework, which is doing ggplot templates. Let's say you have some particular way you like your charts to look, and the style is something like this. So in this case, I'm going back to the Gapminder data. I'm going to generate a plot. That is, the Gapminder data filtered down to Afghanistan. It is going to be X. The x-axis is year. The y-axis is population in millions. So pop divided by 1 million is pop in millions. I like my lines to be fire brick red. I like there to be no X label. I like my Y label to say population millions. And population of Afghanistan since 1952 is the title for the whole thing, using theme minimal. And I have made my plot title extra large. This is how I like all my plots to look like. Well, if that was the case, how would we make this so it would work for any arbitrary country we gave it? Anyone have ideas? What would have to be flexible in this for it to work for any country? What was that? The filter. First thing. So it says filter country equals Afghanistan. Well, if I want it to be able to be any country, this needs to be a variable instead of just Afghanistan. We could say like country equals country, and outside of the function, inside the function when I call it, I would have to assign a different country each time. So that would make it flexible. But what else would have to change? So I could change that, but the problem is, what else would still be the same? So the title would still say Afghanistan. We don't want to say Afghanistan anymore. I want to say whatever country is there. So we have to use some kind of function that would take this text, population of, and since 1952, and insert a country name in the middle here instead of Afghanistan. All right? But we can do that. We've actually used functions to do that throughout this class up to this point. How could we make this flexible for any Gapminder variable? So in this case, we're doing population. What would I have to do to make it do something other than population? Where would it have to change? The y. So we could make it change the time, but y, we would have to say down in AES here, y, we could change that. We would also have to make it so it's no longer dividing any of them by a million, but we'd have to make this flexible and change. And then did you say the title? Yeah. You'd also have to change the title. This says population in millions. Well, we want this to say something other than population millions. We have to say whatever the variable is we're giving it, right? So to make this flexible, we have to have a bunch of different things that are variables instead of being a constant. Okay? So this is what this base plot looks like with Afghanistan. I don't know why this would justify being somebody's favorite plot style, but maybe it would. It's very clean. Okay, here's another example. We want, say, to be able to do this same plot, population of Afghanistan since 1952, swap the country, Peru, swap the variable life expectancy, but still call in the same function, still run all that without typing any of that code over again. Okay, here's a way we could do that.
I have a question.
Yes?
So with regards to dividing the population by a million, if I wanted to create a function, if I wanted to make this flexible but generate a function that would constantly divide something on the y-axis by
Yeah.
a million or 10,000, because I'm working with a lot of rates, is that something that I could do?
Be trivial. Yeah. Yeah, absolutely. You can do it just basically like this. So you can make it so that inside the function, take the input variable and divide it by whatever. Super easy to do.
Okay.
So the way you're currently doing it, just put that inside of a function that'll work the same way. Any code that runs outside of a function will run inside of a function the same way. Okay. So to make this flexible for country, I've altered two locations inside this function. So the first thing is now, we're going to make a new function. We're going to call it Gapminder life plot. So this is going to be life expectancies only as an initial example. It is a function of country. You just give it country. It goes and gets the data, whatever, but it filters down to the specific country. So I say it is a ggplot, Gapminder data, filter down to whatever country we give it. Country equals that, which means country is going to have to be some quoted text that is a country name, which is just going to replace this in this equality. AES, our X is going to be year, or Y is going to be life expectancy. We're not making it flexible for those different variables yet. It's going to be the same geom line, it's going to be the same X label, the Y label is life expectancy, theme minimal, but then we have to do this. GG title is now, GG title, paste some text together. The text is life expectancy in space, the country's name. So country here is some text, right? Well, we can just insert that text right here too. Space since 1952. Everything else stays the same, right? So what the country argument we're giving this function is doing is two things. It filters to a specific value of country, and then it adds a text value in GG type. Does two things. I can do this. Now I can say gapminder life plot, country equals Turkey. It automatically says life expectancy in Turkey since 1952, and this is the country of Turkey's life expectancy. We've made a template. Now we can have one function call, and it has all of this code encapsulated in one little function. Kind of neat. This works. Okay? Next thing we want to do is let's make the y value flexible. This is something somewhat more complex because we have to change a bunch of things to make it work, right? We need to change the title text, and we need to change the y-axis label, and then we actually have to change which variable goes into the plot inside of the function. So the first thing we're going to do is inside of this function, we're going to create some sort of what we call a lookup table. That is, we specify a variable name for this function. Given that variable name, it's going to go look up some text to assign to the y-axis label and the title text. So we're going to create named vectors. So for each variable in the data set, they are life expectancy, population, GDP per capita. We have text we want to insert into the y-axis. So when the variable is life expectancy, we want to spell out life expectancy for population in millions. GDP per cap, we have to say GDP per capita, comma, USD. So these are the actual variable names on the left, which are the names of these elements. These are the actual elements in the vector. So this is just a vector of text with these names. Same thing for title text. Life expectancy, pop, and GDP per cap. The actual variable names, but then some different text. So title text, life expectancy in, which we can attach to the country that we have, and then some remaining text that is by default in from 1952. Okay? An example of how this works in the function, if I say y-axis label and subset it to the population, the text that pops out is population millions, which is this right here. If I subset title text also to pop, it returns population of blank. Does that make sense how the subsetting works? We're using the variable name to get out the text that we want, which we're then going to stitch together into our titles and our labels. Okay, so the complete function to do this looks like this. To do it, we're going to take advantage of something called AES_string. So you know in ggplot we use AES to do aesthetics in something, but we do it by saying something like x equals a variable name, but that variable name is not quoted. In ggplot, at least up to the last time I checked, they might change this, you can't use a quoted variable name in AES. Instead, you use AES_string, and then all your variable names need to be quoted. That's perfect for our function here, because we're passing a quoted variable name, not the actual object itself. I'll show you how that works. So, our new gapminder plot is a function of country and a y variable. Inside of it is that lookup table we specified before. This is the lookup table. But now what we're doing is we're saying our y-axis label is equal to that vector lookup subset to a y variable. So if, for instance, if my y variable is pop in quotes, it goes to this list and says, oh, there's population, and then to y-axis label, assign this value, population millions. So this is population millions. For title text, look for pop. Look for pop, it becomes population of. So for the rest of this function, anywhere y-axis label is encountered, it will be replaced by population millions. Anywhere title text is found will be replaced by population of. That's how the lookup table works. It temporarily sets some variable value. Okay? Next thing that's changed is, well, this is the same as before, gapminder, filter, country equals country, just as it was before. But then down here, inside the ggplot, the AES is AES string. X is year, because we're always using year as our x-axis. But now y is yvar. So yvar, our y variable argument up here, if it was pop, it would be pop. Population would be our y-axis. Then, in title, our title is now pasting together title text, country, and since 1952. So for population, it's going to get title text pop, so population of, let's say it's Afghanistan, country, Afghanistan, since 1952. And it's just going to stitch all those arguments together, and otherwise reuse all the same code as before and generate something. Make sense? Questions about that? It's a lot going on, but you could kind of poke at it and see what happens. Now we can do stuff like this. Gapminder plot, country Turkey, yvar population. And now it says population of Turkey since 1952, population in millions over here. Could do it for any country. Do I do it for another one? No. Okay. Pretty cool. Now you can just have template one. If you need to generate a lot of similar plots, just make a template. This one is incredibly flexible. It works for different countries and different years. You might not have to be that flexible, but you have a lot of power to do it. You're going to be basically replicating this, but a slightly simpler version in part 2 of your homework that goes out today. Questions? Okay. So, sometimes you write a function or be working on something in R, and it just breaks, and you can't figure out why it breaks. This is especially common writing your own functions when you don't build in lots of error messages. It will just fail in some totally opaque way. R has built-in debugging functionality. If you do something like say a function you want to debug, you say debug that function, the next time you run that function, it will run it step by step through every line of code inside of it until it errors out. That way you could see where the function is breaking. Go through, go through, go through, go through, and then it'll pop out when it gets an error. You can trace through all the errors run inside a function. Okay? It will do that every time you run that function until you undebug the function. So if you've written something relatively complex, this is a good way to run through all the code and figure out where your errors are. Okay. So anyway, I'm going to wrap back around to the first thing I talked about today. There is a process that I recommend for the general practice of data processing. So data processing and sort of project management working on actual data can be really, really complicated, and there's usually approximately an infinite number of ways to approach any problem. The general approach I think people should take, because it's the approach I take, and of course that makes it right, the approach I think people should take is something like the following. First thing you want to always do is sit down and look really carefully at your starting data to figure out what you can actually get from them. Look at your data, know them really well. And when I say know them well, I don't always just mean, say, run structure on it, view your data frame, things like that. This really includes, for a real research project, it means reading the code book of your survey, finding your data sources, that kind of stuff. Know your data inside and out so you know exactly what it is you're working with. Have a good, clear picture of it. Know, before you come up with exactly what you want, the end goal, that something that resembles what you eventually want is even possible, right? Then determine precisely what the end product looks like. And when I say precisely, you may even want to build a fake example of your end product. Say you know you want your data frame to look a particular way, create a fake version of that one with, example values in all the different columns, all that kind of stuff. Something small. Maybe it's just maybe it's going to be 8 columns and 10,000 rows. Make 6 rows of those data with the same columns and what the value should actually be. Look at it. That way you can picture it, you can keep displaying it and be like, okay, this is what my end product should look like. Then identify any individual steps that are needed to go from this thing 1 to this thing 2. You should have a very clear picture of them, so coming up with steps should not be that difficult. Make every discrete step its own set of functions or function calls, and if any step going from 1 to 2 is confusing in any way, it should be incredibly obvious. If it's confusing in some way, it should be broken up into more steps. Lots of steps are fine. You should be able to logically know what is happening in every step. dplyr makes this really easy because you can just chain commands together. You do one thing, you've taken one step. You do the next dplyr command, you've taken the next step, so on and so forth. You might have hundreds of commands, but you should be able to look at every step and be like, well, it looked like that, now it should look like this, now it should look like this, now it should look like this. And you can test it as you go because you should only be writing and running one line at a time. One of the biggest problems people run into is they'll write like 3-4 lines of dplyr commands. They get some weird shit out. No, just do one line at a time, unless you really know what you're doing. Okay. Then complete each step separately and in order. When I say this, I mean do not ever move beyond doing some particular task in it until the step that you are on is producing exactly what you need for the next step. You stop, you do it. If you do not have exactly what you want and you move on to the next step, if you put garbage into something, you get garbage out. Make sure the step is producing exactly what you want. Then when it gets what you want, it might be slow, but it's what you want, then move on to the next step. Never worry about combining steps together for efficiency or for speed until every component of the entire process works. The only exception to this is if you're working with data so large that you need some efficiency to get it to work at all, like to get it to produce something in less than a couple days of processing time. But generally, no. Efficiency is the enemy of getting shit done. Okay. Once you are finished, once you have every step producing what you want and the final product coming out the way you want, if you want to do this again, convert the prior steps into their own functions to make it efficient or speed it up. But that is a last step. That is premature optimization. There's no necessity to do that unless you have to, and you're going to be doing it a lot. You follow this process, it involves upfront work. Upfront work can be a huge pain. There's a mental labor involved in sitting down and coming up with these things when you're like, I should just be able to poke at it and have stuff come out. That is how you waste your time, probably very large amounts of time. Upfront labor will save you a lot of downstream headache. Design your code before you actually start writing anything, and you'll have better results. Okay. Your homework is to download and analyze data from the first year of Seattle's failed Pronto bike sharing program. This is a data set commonly used as a sort of data science example thing. It's a nice data set. It's actually fairly clean. You can do a lot of stuff with it. Using the provided template on the website, you're going to write a loop to read the data in from multiple files. It's only 3 files I want you to read in, so you could do it manually, but the instructions are explicit. Do it with a loop, because you got to learn loops. You will write functions to clean up the data and use those functions, and then you will create a function to visualize ridership over the first year so that you can give it some basic arguments like, oh, is it raining or not raining? See what the ridership looks like just by giving it an argument about the rain. There is some string processing needed, that is text manipulation needed. You should have seen most or all of it already from my lectures, but it's easy for me to have breezed over it. So you should be able to like Google it or remember it a little bit, but if not, some of it will be covered in next week's lecture. I give very specific suggestions in the template of functions to use, but if needed, I can cover string processing in detail in lab, or I should have removed that because our lab is not occurring on Monday because it is Veterans Day. So, yeah, this is a homework that quite possibly I will give an extension on because there's no lab and because Part 1 and Part 2 together are the last homeworks in this class that are actually graded. Normally, everything from here on after that is extra credit, because in this class I don't want you guys doing homeworks for my class when you're writing final papers and projects for your other classes. Okay. That is everything for today. Any questions? The darkness has everyone quiet today. Yeah.
Can I see how the debug function works? I was trying to not work getting it yet.
Yeah, okay. So, let me see as an example. Let's go, okay. Test data, I'm going to want... Okay, so we're now in debugging mode here. So this is saying it enters the filter function and it says debug, use method filter. Next, use method filter. Now it's going inside this function. It's saying, okay, the input as data.frame filter table df data. Okay, debugging inside of that function. Oh, use method. Use method. Now we've got an inside of another function that is inside of another function that is inside of another function inside a filter. And these are all the different things that are being run on whatever input it is. Okay. 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 This shows you how many operations occur until the filtered output comes out. That is every discrete, like, running of some object inside of the filter command, step by step by step. You can see filter actually does a whole lot of crap underneath the hood because we've stepped through it. But debug shows every single one of those steps. So you can go step, 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 and then suddenly if one of those steps fails, you know exactly the step, and you are currently looking at the code that just failed. Now, debugging. Then if you want to get rid of that, undebug. Okay, and now it will run and just produce that output without running through all those steps. Debug's kind of neat. It's debug functionality built into that, like most scripting languages. Python has a similar one, but I forget the name of it. Yeah, I don't use it a lot, but it's very useful if you have some weird bug, especially some weird bug that only happens with specific values you give it. You could put in those values and see where it fails. R also has some built-in traceback bug detection functionality too, that when you run something, it will trace it back through the steps. But, yeah. You're all free to go, by the way. You don't stay here on my account. Yeah. Any other questions? Mr. Brown? Cool beans. I can go enjoy the darkness. Makeup lab? Yeah, I'll either do a makeup lab or just delay the homework. I'll do one of the two. I'll figure it out.
Oh, okay. Okay. Yeah,
I might just delay it a week because
okay. Because we don't have.
yeah, we don't have lab, and then Thanksgiving is gonna fuck up stuff later. So I don't want to like punish people.
That week before Thanksgiving, we don't have class. The Wednesday before Thanksgiving.
Oh, we're gonna have class.
Oh,
It's just
okay.
nobody needs to show up. Because I'm just gonna, that lecture currently is the geospatial like mapping lecture, and it's not like required for anything, so it'll just be
Okay.
like you can show up if you want, if not, watch the video.
Okay.
Yeah. And I actually have to completely rewrite that lecture anyway because Google just changed their map API and fucked my entire lecture. But yeah, I found that out today.
Is it possible that I didn't receive any peer review for the past 3 weeks?
Okay, so you've received no peer reviews? Have you received? So you had.
I received a report for mine, but I didn't see any other peers assignment.
Oh yeah. But did you get a point for it?
No.
Okay.
I
So
didn't see the assignment.
okay, email me.
Okay.
Email me and I'll check on that. Yeah.
Okay.
Yeah, it might be a problem or something. I'll figure it out. Okay. Yeah.